One important application of the normal distribution involves evaluating the results of a sample. If we take a sample and calculate information from the results of that sample, that is called a statistic. And there are a variety of things that we can calculate based on a sample. But for today, we're going to be discussing X bar, which is the sample mean. If we want to calculate X bar, okay, we take and add up the individual results. So if I've calculated n individual observations of a particular process, and maybe I'm measuring the length of something, the time it takes to do a process, something that I'm measuring, or even that I'm counting, I've got values for that random variable n times. I add up those values and divide by n. Okay, basic arithmetic mean to calculate X bar. Now you notice that when we talked about a population, we used mu to represent the population mean. Greek letters represent population parameters. Latin letters represent sample parameters. So we see the X for our sample. We used mu for our population. Now this value is a random variable. X bar is not going to have the same value every time. If I come back the next day and take another sample of n observations, and the day after that, and the day after that, each of those is going to give me a slightly different value of X bar, okay? Because the numbers I'm selecting, the population I'm selecting from is random, and so I'm going to get different values every time. And so X bar is a random variable. Just like our X is, we can find the probability that X takes on certain characteristics, that X is greater than a certain value or less than a certain value. We can say the same thing for X bar. Now, X bar, just like some random variable X, has a mean and has a variance. The mean of X bar, the expected value that I would look for in sample mean, is equal to the mean of each of the individual samples. Okay? I've got n samples, each coming from, I have n samples. This came from a population with mean mu. So did this, and this, and this, because they all came from the same population. And so their individual means are each mu. And I divide by the number of samples. The mean value for X bar, or the expected value for X bar, is the same as the expected value for X. And logically, that tells us that as we take a sample, the average of that sample, or the mean of that sample, is the same as the mean of the population. Now, variance works a little bit differently, because the variance of X bar is equal to the variance of each of my individual variables. So I take n samples, add up their individual variances, but I need to divide by n squared, because this is my parameter squared. We took x minus x bar, remember, when we were calculating sigma. And so I have n sigma squareds in the numerator, but I have n squared in the denominator. So my result is those n sigma squareds divided by n squared. The variance of x bar is sigma squared over n. Mu, it was the same. Mu of x and mu of x bar are the same. For sigma, sigma squared of x bar is equal to sigma squared of x, of my individual random variable, divided by n. And what this, if we think about the distribution, we can see why why this behavior occurs. If I have a normally distributed random variable, it's not unusual for me to get a value down at this end. Okay? That I have a value of x, I'd have a reasonable probability of getting a value that low. But in order to have x bar that low, I would need to have multiple values all occurring in this range in order to give me a value of x bar that is that low. What's more likely is that I'm going to have multiple values distributed around the range. So I may get one value down here and one value here, but I'm also going to get values at either end and lots of values here in the middle. And so x bar is more likely to fall somewhere in this range, this narrow range, following a distribution something like that. So the mean is the same as the mean of x, but the variance, it's much narrower, because as I take a sample and as my sample size gets bigger, we see that our variance decreases even more, as we see that n in the denominator, as my sample size gets bigger, my variance of sigma square, my variance of x bar gets even smaller. So the bigger the sample size, the narrower this distribution becomes. So what we might do is calculate the probability of getting a sample mean that's less than or equal to some value. In order to solve this, maybe we have a sample mean that gives us a value of 12.5. What we want to find out, what's the probability that our sample mean is 12.5 or even less. We would solve this the same way as we've done any other problem related to the normal distribution, where we transform our x bar into z. The difference is that in the denominator, we subtract mu, because mu is the same for x and x bar. In the denominator, we take the square root of our variance, sigma squared becomes sigma, and the n in the denominator becomes the square root of n. And so that becomes our denominator. We would simplify this expression to find what value of z we need to look up in the table, and then we could find that probability to find out the probability that our sample mean falls this low, as opposed to the probability that a single observation. If we want to find a single observation, the probability that one time I collect a sample and it falls at 12.5 or lower. In this case, we're looking at the probability for x. We still transform to a standard normal random variable in terms of z, but now our denominator would only be sigma, because we're looking at one value. We wouldn't need the square root of n. If we did include a sample size of 1, the square root of 1 is 1, and so we end up with this expression anyway.